Hello, and prepare. I'm going to rock your world with this quick description of raster modeling. You know that you can use raster surfaces to map a lot of different things, like population density, land cover, temperature, slope, elevation, crime density, even discrete features like roads or water sources, or even better yet, cell values that represent distances to roads or water sources. So let's say we want to calculate and map areas that meet certain input criteria. For example, maybe we're mapping habitat for a certain species and we're basing suitable areas on inputs like preferred land cover, high elevations, and availability of certain food. Or maybe it's human habitat, like suitable walking distances to amenities, maybe require at least 10 inches of annual precipitation and a surrounding neighborhood area with an average slope less than 2 degrees. The first thing you need to do is simplify the values in your input rasters. So the idea is to simplify this broad range of values into simple classes of suitable or unsuitable designations. The values can be either continuous values like these, slope, elevation, density values, precip, distances, or they can be categorical values like land cover, where the cell value represents a plant type. Remember, with rasters, you get a value and a count, and the value represents, it can represent something categorical, like a plant type. So these suitable and unsuitable designations that we're trying to create are called binary outputs or a true-false style output. And just going back, these categorical raster values are much less common than continuous rasters, but they are really important to understand when we do things like reclassify. Okay, so the idea is we're going to take something like slope and say, okay, this cell falls into the range of suitable slope for my habitat, so I'm going to assign it a 1. This cell is not suitable for slope, so I'm going to assign it a 0. And now you have to do that for the whole slope raster, and you're going to do that using the reclassify tool. Of course, whether something is suitable or unsuitable depends on what you're trying to map. Maybe you're mapping areas with elevation greater than 4,000 meters, slope less than 20 degrees, or you have a range of values that represents the size of watershed that you're trying to map. With categorical values, you have to be careful and find the specific land cover types that you're interested in and assign those specific raster values to your true or positive suitability value. Okay, so here's an example of the reclassify tool. We're going to start with slope, for example, where we have a range of values from 0 to 90 degrees, and we're interested in mapping areas where the slope is greater than 45 degrees. Here is the reclassify tool in ArcGIS Pro. Input the slope raster. It's going to default to the value field. Remember, raster attribute tables give you a value and a count, like a histogram. But you can change this if you have something else in mind. Then you're going to put in your classes, and remember, we're interested in slope greater than 45 degrees, so 0 to 45, we're going to give the false value of 0, and 45 to 90, we're going to give the true value of 1. It's really important to have data or a value assigned to your unsuitable cell outputs. Okay, and then when we run that, we end up with 2 output values, false and true. So these are areas that are less than 45 degrees, actually 45 degrees and less, and the ones are 45.01 to 90. These are the high cell values. That's how ArcPro treats these. So if you put in the same number here, this includes 45, this one is 45.01 and up. Okay. Once you have true, false, or suitable, not suitable versions of your input surfaces, you add them together using the raster calculator to find areas that are very suitable or very not suitable. If you have 2 inputs and you add them together, then output cells with a value of 2 would be cells where both inputs are suitable or true. You could add a third input surface or variable, and the output cells with the value of 3 would map locations where all 3 input criteria are being met. In this example, we have slope and elevation, 0, not suitable slope, 1, suitable slope. It doesn't really matter what that represents in real life. Elevation, same thing. 1s are where our elevation criteria are being met, and 0, they are not. When we add them together using the raster calculator, you can track it through. 1 plus 1 equals 2, upper left corner. Upper middle, 0 plus 1 equals 1. 0 plus 1 equals 1 for the upper right corner. So cell sizes have to be the same. You need the same resolution, and they need to line up. And we can talk about that in another video. Here's the catch. What if you wanted to know which cells are suitable for slope in particular? Like, what if we really needed to know whether slope was being met because that was a real deal breaker for our habitat modeling? How could you encode these inputs to be able to tell from the outputs which variables are being met? For those of you who are thinking to yourself, I'd use orders of magnitude. You're all geniuses. That's exactly right. Here's the same setup. So here's our slope, and we're going to use 0s and 1s, excuse me, for unsuitable and suitable. But for elevation, let's use 10. You should be able to predict the range of output values from this. And I should make you all just call me and tell me the answers so I know that you get it, but don't actually do that. So 0 would be the cells that are not at all suitable. Neither criteria are being met. 1 equals suitable for slope, but not elevation. 10 are suitable for elevation, but not slope. And 11 are the cells where both inputs are being met. But this way we know which ones are suitable for slope. You can see that we're actually making some headway here, right? What if you wanted to add a third surface variable like land cover? What would be the suitable value for land cover? What would you encode this? If 0 is going to be unsuitable, it always is, what would be the value that represents suitable land cover? And for those of you who are shouting at the computer, 100, you're exactly right. And you could see that we could keep adding variables with bigger orders of magnitude. We could add distance to water as 1,000. We could add, you see where I'm going with this. Okay, our range of possible output values now would need to include 100, which is suitable for land cover but nothing else, 101, which is suitable for land cover and slope but not elevation, and 111, which, shaboom, would be suitable for land cover, elevation, and slope. We're adding them together. I hope this makes sense. This is so powerful. I'm going to let you look at that for a second. Okay, now for the big money model. And you can tell this is the big one because the background changed to a gradient fill. This concept can be expanded to include non-binary inputs. They do still need to be classified, but you can even do this with the continuous range of values as long as you know what you're doing. But I think that classifying them into these representative cell values makes the most sense. What if we wanted to increase the complexity and have classes for slope suitability, not just true false, but 0 unsuitable, 1 mildly suitable, 2 moderately suitable, and 3 perfect suitability for slope? What are we going to do when we add a variable? 0 is always going to represent unsuitable. We've already decided that 10 is going to be maybe our mildly suitable. So here's the first test question. What value would indicate moderately suitable elevations? Would it be 11? Would it be 20? For those of you who are shouting 20 at your computer, you are absolutely right. So to carry this forward, the range of values for elevation would be unsuitable, mildly suitable is 10, moderately suitable is 20, and perfectly suitable elevations represented with 30. Let's go for it and add a third variable to the model. What would the values look like? Yes, they'd be in hundreds. That's our orders of magnitude for adding a new variable. So what are the classes going to be represented with? 0 for not suitable, 10 mildly suitable, 100, 200 moderately suitable, and 300 for perfectly suitable land cover types. Makes sense? We're going to add these three surfaces together. Can you predict the range of output values? I started writing them out. 0, 1, 2, 3 would be cell values where only slope is suitable. Neither elevation or land cover are suitable. These 10s, just 10, only elevation. 10, 20, 30, only elevation is suitable. But 11, now we're talking about elevation and slope being somewhat suitable, but only mildly, mild and moderate, mild and perfect, moderate and mild. Does this make sense? And I just kept going, but then I got tired of it. So here's our output. If you add these three surfaces together, 333, that's our cell value that we're looking for. That's the one that says all three criteria are highly suitable. Okay, here's a test. What would a cell value of 103 represent? Again, I should make you call me and tell me the answers so I know that you get this, but don't. 103. 100, mildly suitable land cover. 0, not suitable elevation. 3, highly suitable slope. Awesome. That is the beauty of raster modeling in a nutshell.